it's time to begin. I will try to move around so that I don't block everybody on this side. Let me know if I'm in your way. Welcome to the talk, Using Mathematics to Deepen Understanding of Scientific Phenomena. I'm Pedro, and this is work that is ongoing between the company that I work for, Apprentice, Rutgers University, and also University of Colorado Boulder. And just a real quick introduction about what we're going to talk about. But first, we're all here. We're all healthy, hopefully. Hopefully everybody's been okay this school year. I know it's been rough. Have the students been all right with everybody? I heard someone say that 9th graders were acting like 6th graders. I think this is like a common.
Wait, they're getting better?
Sorry. I'm hoping that COVID hasn't taken a toll on everybody's life, aside from the inconvenience of masks and whatnot, that, everybody's lives have been happy and healthy to the best that they can. So, a little bit about me. So, I've been working in science education for, when is it, 2022? So, about 15 years. Prior to that, I was a defense contractor, so I joke that I have gone from making bombs to educational software. But I actually got my doctorate in how middle school kids learn science inquiry and conduct science experimentation. And so from that work, working with my advisor, Janice Goldberg, we tried to spin this off into a product that also is ongoing research right now. The work that I'm going to talk about has been funded for years by the Department of Education and the National Science Foundation. And so this is work that's near and dear to my heart. I've been working on this since there was no software whatsoever. And now we've scaled to kids having done over 1 million labs. And so the other things that we're going to talk about today are, what does using mathematics look like when students apply science practices? And how is that different from maybe things that we've done for years and years? I know when I took science eons ago, it was a lot of formulas, plug and chug and stuff like that. But how have the new science standards changed that, and what does that look like? And from there, we'll talk about what strategies can I use to help my students apply mathematics while they're doing more open-ended investigations. And we'll talk about some studies on how feedback that we've been able to give teachers can help improve student learning. So just to give you guys a context, is that the system that I work on is called Inq-ITS, Inquiry Intelligent Tutoring System, and like I said, this has been ongoing work for 15 years. And essentially what they are virtual labs that score themselves. They score not only what kids are doing in the interactive labs, but also their writing using claim evidence reasoning. So automatic scoring of the doing of labs and the writing. And they work on any system, any internet-enabled system, and for grades 4 through 12. And basically it's got some really neat features to it that while kids are working in real time on their devices, we have two means of feedback. We have an integrated virtual tutor that gives help as students are working, that helps them get better. But we also give you real-time reports and alerts that let you track how students are working, and immediate feedback to let you know who is struggling, so like a magic crystal ball, and you'll see an example of that later today. And when you employ these two modes of feedback, students are able to learn science practices and apply them to new science topics even 6 months later to new science topics, right? So they're able to transfer what they learned in one science topic, doing science inquiry, to another science topic. And what I'm going to focus on today a little bit is some of the virtual labs and some of the alerts and how we apply this to using mathematics, which is really new research for us. We've started off in the middle school arena, and we haven't really focused on how students use mathematics, so you guys are seeing some of the newer research that we've been doing. Who here is NGSS and who here is Texas Text? TEKS. NGSS, anybody? Okay. Texas? Anything else? Oh, what are you?
Virginia Standards of Learning.
Okay, are they different from all the others? Okay, then I apologize.
Thank
you. So I don't have any background knowledge in the Virginia stuff, but I can at least talk a little bit about NGSS and text. So they talk about these things called science practices, and if you're in NGSS, or processes if you're in text. And more or less what they are the ways that students or scientists go about doing science. And it's very different from the content, right? The background knowledge and the content knowledge that you need in order to conduct inquiry. But these are more like the practices of science. How do you act and think like a scientist? And I know there's a lot of words up here, right? But they're basically things like, how do you form questions? How do you form hypotheses? How do you develop and use models? How do you explore limitations of models? Plan and carry out investigations, design controlled experiments, use mathematics, make explanations, communicate your findings, right? They're all very similar. If you're in Texas, I don't know if anybody's actually read the standards in Texas, that I kind of had to summarize the common themes throughout all of them, because depending on what science topic you teach, the practices or the processes actually differ slightly. So these are just the common themes. But as you notice here, right, there's actually a fair amount that focuses on mathematics, right? When you're analyzing and interpreting data, right, you're essentially using mathematics, you're using your data science knowledge. But then there's also, using computation, using algebra, all that sort of stuff. You're organizing, you're making predictions from trends and data. You're using mathematical calculations to assess relationships, right? And even some of the other practices like asking questions, using models, and planning and carrying out investigations. When you involve mathematics, all of those other practices also get affected as well, because the nature of the inquiry itself also gets more complicated. And I'll talk a little bit more about that as we go along. So, why incorporate mathematics during an investigation? Well, so the bottom is like the standards require, right? So we already know about that. But we also know that mathematics is a tool that you use, and it's key to understanding science, right? It enables you to make predictions. If you're able to formulate mathematical equations, if you're able to graph your data and link that to some physical phenomenon, it unlocks a lot of understanding, right? If there's a linear relationship between, like, say, force and acceleration, right? That actually gives you a lot of power to understand, like, what happens when you increase more force, what happens to the acceleration. But also, I'm not sure what level everybody here is, elementary, middle, high school. This talk is going to be a little bit more geared towards later middle school and early high school. But poor math skills are critical to high school science, right? I think we all know that, right? And especially now that COVID has happened, I'm guessing students' math skills have dropped significantly this year. Is that a fair statement to say? Yeah. So you're ninth. So out of curiosity, like what kinds of difficulties with math have students been having in your days?
I think it depends on the grade level. Like for middle school students, it's division and multiplication.
Mm-hmm.
Like you can go back 2 years and look at fundamentals 2 years prior and say that's where the gap is, or that's what's fueling the gap in our middle school.
Got it.
For Texas.
Got it. And so how that impacts science then is, if I'm guessing that if you have to do a lot of ratios and proportions and that sort of stuff, percentages, that they're in trouble, right? And that's one thing that you actually have to do as part of using mathematics and science. Anybody else?
Well, I think just graphing in general.
Graphing in general, that's difficult for students. Anybody here teach physics or chemistry where they have to use algebra? How's that working?
Yeah, they can't rearrange formulas.
Can't rearrange formulas. How are they at plugging numbers into formulas? Are they okay with that? No, I see. No, right? Same thing, right? It's again, you need to apply multiplication and division, and if you're lacking those skills, what do, right? And if you don't have those skills, how can you access higher level science? How can you access your STEM careers? But I actually do point out too that plugging and chugging of row formulas necessarily doesn't lead to deep content understanding, right? And part of that is because you can just learn to apply those things blindly, right? If you're given a force and a mass and you're asked to compute the acceleration, right? Students know F is this thing, M is this thing, right? And they know to divide. If they've got the skills, right, they know to divide, and they might not actually be thinking really deeply about what does this actually mean? What does that F actually represent in the physical world? What does that M actually represent in the physical world? And what does that say about making predictions? And so these are the kinds of skills and competencies that the new science standards are trying to get kids to understand, to really deepen their content understanding with using mathematics. And these are also the types of competencies that we're trying to measure and trying to help you empower your students to learn. But guess what? I think we've already alluded to this. It's pretty hard to do this, right? So the standards say one thing, but actually doing this in reality is very difficult. And, well, there's a good couple of reasons why. Does this look familiar? Maybe not. Maybe it doesn't look familiar. Why? Because we've been working remotely. So I'm guessing, well, this is probably all these students working in the room would be a great thing nowadays, right? And using stuff remotely has probably exacerbated this problem. How do you keep track of what students are doing? How can you even do an open-ended experimentation remotely, right? Has anybody been able to do any labs while working in a remote situation? Okay, how have you done it? I'm actually curious.
Well, we've been back this year, but we were on Zoom and I just live streamed myself, rolling balls, doing things like that, and then kids getting the data off me, or I made a video and then they were able to get the data off of what I was doing.
Oh, awesome. Okay, so they weren't doing the experiments themselves, but you were able to actually get them to do some science practice.
Well, if it was basic stuff, I knew they had it at their house.
Okay, cool.
Yeah. Like,
That's awesome.
like for gravitational potential energy, dropping a tennis ball, something like that.
Awesome. That's excellent. And then you were able to watch them do that sort of stuff and like have them analyze the data and you can go through and grade it and all that sort of stuff. That's awesome.
Had to get creative, right?
Yeah, you do. Did anybody else do something similar?
We can do motion experiments and video analysis, we just go and shoot our video outside of the
Got it. Did anybody have students do lab write-ups or anything like that during COVID, or was that even more difficult?
So I still actually teach some classes virtually, and they
Oh,
have,
wow, okay.
yeah, that's great. But no, they get about 12 lab options, and they have to choose 4 of the 12, and then for those 4, they have to do a full lab write-up.
Out of curiosity, was it worse to do full remote or hybrid? I hear a lot of hybrid, yeah, because it's a little of everything, right? I'm guessing you had to do double the lesson plans. That sounds exciting, right? Thank you guys for doing what you do. I know it's been a rough couple of years. Okay, and so, right, so you've got one major problem, right? That, how do you keep track of what everybody's doing, either remotely or in person, right? And remotely, it just exacerbates the problem, but we know that students struggle in many ways, right? And we've talked about this. Some of you have already alluded to this about having difficulty with division and multiplication. Someone mentioned earlier about making graphs. And there's a whole world of literature on this, and this is just like a sampling of some of the things that students have trouble with, right? When they make graphs, they have trouble choosing what to put on what axis. They have trouble choosing what data to plot. If you've got lots of data to choose from, what goes on, what's my x value, what's my y value. And also, they have trouble linking what's in a graph with what's in a data table. So even though the data table is where they might be drawing their graph data from, they still have trouble understanding what those things are, and then linking that back to the physical phenomena. They also have trouble finding trends in data. I'm guessing things like linear versus nonlinear. Nonlinear will blow their mind, right? Has anybody been able to bridge this gap? I'm just kind of curious about dealing with nonlinear phenomena. No, okay. So then hopefully we're in the right place. They also have trouble when they find trends in data, understanding what the y-intercept is and what the coefficient, that the deeper the higher the coefficient, that the more steep a curve is or something like that. And again, relating data to tables. If your students are learning, if your students are in algebra or not, right, there's a whole host of things I've already mentioned, that linking the equations to graphs, linking the equations to physical phenomena, understanding that this variable represents some physical quantity, and they have trouble just manipulating equations. But then there's this other aspect too of working with mathematical models, right? And this is sort of an undertone, right? That even in a mathematical equation is a model, right? A graph is a model, a data table is a model of some of the data as well, but an equation is a mathematical model, right? It's something that has limitations. It's something that has assumptions built into it, whether stated or not. It's something that you can use to make predictions, right? Understanding that's a really powerful tool to understand it. It's not just about plugging and chugging. It's a language that you can use to talk about science in a really rich and deep way. They also have trouble using mathematical models to form arguments, and also have trouble refining them. Then saying, okay, now that I've got some new data, how can I change up my mathematical model to make it more aligned with the real world? Right, so there's a whole mess of stuff. And in the work that we're doing right now, we've started off with the making graphs and the finding trends in data, and we are moving more towards interpreting equations and working with mathematical models. So I'm just going to focus on the first 2 today, but I'm fully knowing that the other 2 are just equally important. So I'm going to give you guys an example activity that we have been working on, just to sort of highlight what it would look like to have kids engage in this sort of deep scientific inquiry while applying mathematics at the same time. And I'm going to preface this by saying one of the goals that we had in designing this is that this is something that we iterated with teachers and students on over multiple years. And the cohorts that we worked with typically struggled with the algebra. They didn't necessarily have the algebraic skills. So we tried to pull back on that and to give kids some scaffolds to help them start to understand that algebraic reasoning while not making it a requirement to do these kinds of activities. Let me just take a drink real quick here. Also, can everybody hear me okay?
Yep.
Okay, great. I know this thing is rough, and I'm probably going to lose my voice halfway through. Okay, so all of our labs kind of have a similar look and feel to them, and they all start off with an introduction, and I'm going to have everybody kind of walk through this with me. So this is one on Newton's law of gravitation. So this is understanding about like how the gravitational pull between objects, like two masses, sort of attract each other, and what the gravitational force is, right? That F equals GMM over R squared. If you high school, if you're familiar with that. So in this lab, you'll be able to weigh gold bars on planets with increasing mass and increasing orbital distance. And you're going to explore the impact of the planet's mass and orbital distance on the mass force and gravity in space. And to see how these variables will change, you're going to be able to manipulate different variables in the simulation. And I'm actually going to turn over to a interactive view of this, just so that you can, assume that the internet is okay, find out. If not, I'm going to back up. Okay, looks like the internet is okay. So we'll do that. Oh, okay, here we go. Okay, so after doing the introduction, we have this sort of semi-structured inquiry where students are going to form a question, collect data, and then go on to analyze their data. So I'm not sure if you can read this clearly. I think it's a little bit chunky, but hopefully we can work through this. So the goal here is to determine how the planet mass affects the force of gravity on gold. So the first thing we ask students to do is form a testable question. So what do you think a testable question here might be? If I change what would I want to change here to handle this goal?
Distance?
Let's see, okay, you can't read the options. So there's amount of gold, distance in orbit, force of gravity on the gold, gravity compared to surface of the Earth, the mass of the gold, and the planet mass. Yep, planet mass, yep. And so then what happens? Then I'll be able to observe that the planet mass and the force of gravity on gold will have what kind of a relationship? What kind of relationship do you think it'll have? We have horizontal, linear, inverse, square, inverse, square. And we have little pictures next to them. Linear. Some people say linear, that's good. It could be inverse, that's right. So, even when you're forming, so the reason why I wanted you to do this, for a couple of reasons. One is that this is one point that we can have students get assessed on, right? Do they understand the difference between an independent and dependent variable, right? Do they understand what they're trying to change versus what they're trying to measure? But the real thing I wanted to highlight here is that when you're starting to talk about like phenomena in a more mathematically rich way, when you're forming questions, right, the mathematics already comes in here early, right? It's not just an increase or a decrease or a change or a not change, right? I'm talking about like a linear, I'm talking about a different mathematical relationship that you can hypothesize about. And that has implications downstream too of what a mathematical equation might look like and what you might expect to see with the data that you collect. So the mathematics stuff really does hit across all of the different science practices. Okay. Next part here is I have a simulation and I'm able to change the amount of gold, the distance in orbit, and the planet mass. What data would I collect to test my hypothesis? What should I do? Change the what?
Change the mass of the planet and measure the force.
And measure the force. Okay. So I'm gonna, let's see, I'm gonna change the planet mass to be 1, and I'll run a trial. And let's see, so you can't see this well, but I'm gonna read this off. The force of gravity on the gold is 9.92. Okay. What other trials might I run? What else might I change?
Massive gold.
Mass of gold, okay. And now I've increased the mass of the gold force, so the force of gravity on the gold is 38.88 newtons now. What other data might I collect?
So more mass and more nautical like separately.
I'm sorry.
More trials of what you've done.
More trials of what I've done, yeah. So, let's see, what does my hypothesis say? If I change the planet mass, so I should be probably trying to control the planet mass and leaving everything else the same, right? Because I'm trying to isolate on that variable. But here's another question. How much data should I collect? Should I run repeated trials just to make sure that everything is the same, right? These are the kinds of, right? So I mean, we haven't even got to the mathematics stuff yet, but when you are trying to understand mathematical phenomena, these are the kinds of skills that students need, right? They need to be able to collect enough data to see a mathematical trend in the data, right? They need to understand that there might be some noise and variation in whatever data they're collecting, even in a simulation. And as it turns out, this simulation, if I run it multiple times, usually I can get some variation in the data. Yeah, so the force of gravity here has gone up to 39.37. I'll collect a few more, just so that we have enough data. Okay. So I've got 7 pieces of data. All right, next part here, now that I've collected the data, I want to graph it. And so the kind of skills here, right, we want students to pick which data points to graph, and then also pick their axes. So if my hypothesis is about changing the planet mass and observing the force on gravity, you guys can't see this data at all.
If you make it bigger, it almost looks readable.
See, maybe that'll help. Okay. Yay! All right. So the sad thing is, I actually have a computer science background. You think I would know these sorts of things, right? I coded. I don't know how to use it, right? I actually do a lot of software development on this too. So it's like not only am I doing like the educational side of it, I also do the software development. Okay. So let's start off with the axes. What would my axes be? If I'm talking about the planet mass and the force and gravity, what might my axes be? What did I what? X would be what?
The planet mass.
X-axis would be planet mass. And the y-axis would be? Yes. Would it be wrong to do it the other way? Why? That's a very common thing that we hear, yes, that the independent variable goes in the x-axis, and that is actually what we do check. Exactly, that's the other part of it too, is like it would actually not be wrong to do it the other way, it would just be unconventional, and it would actually change the relationship. Yes, but yeah, so we actually do enforce that as well, and this is feedback that we got from teachers, is like, it's really important for them to understand that the independent variable goes in the x-axis. Okay. But again, this is something that students would struggle with. We know this. Students would struggle with this. Okay.
So if the kids put it in wrong, will it make them redo it to get it correct?
We're coming to that, but yes. That is, so actually there is gating factor at each step. We'll get into that a little bit more later. What data would I plot? What data should I be picking here?
The 2 that it highlighted.
So the 2 that are highlighted show the DVs. So what about which actual trial should I pick? I've got 7 to choose from. What should I pick?
4 through 7.
4 through 7. Why?
Because they have the same weight of gold.
That's right. I controlled all those. So actually, Yes, I controlled all those variables.
You could do 3 as well, and 2, because, yeah, because they have the same protocol.
Exactly, I could do those as well. And so, oh, look at that, so I kind of have a somewhat linear view. This is something that's very challenging for students as well, being able to choose what data, because they don't necessarily understand that they should be plotting only control trials. They might know to collect them, but they might know to plot them. There's some other subtle features here that I want to talk about as well. When I started picking points, what happened to the values on the axes? They actually align themselves correctly, so I've got the scales right. This is something that's incredibly challenging for students too, right? That they have a lot of trouble picking what scale to choose in order to reveal mathematical phenomena, right? And what the problem with that is if you have too small of a scale, sometimes you can't actually see what the trend might be. It might look linear, but in reality it might be inverse square. Because when you're localized, right, it might actually look pretty linear. We recognized that this was a difficulty, but what we really wanted to do is have students really see the mathematical phenomena, so we decided to pull back from that and have the scales done automatically in order to keep them focused on the bigger picture of understanding how it links to the physical phenomena. But when you're designing, the reason why I wanted to bring this up to you as well is that when you're trying to do this even in a hands-on lab, these little subtle choices make a big difference in how complicated an activity might be, right? And they'll have downstream effects. If you really want students to understand that there might be a linear phenomenon and they don't understand how to scale their graphs correctly, they might totally miss the point. It's really like, this sort of work is actually really wild to understand how these little subtle tweaks have such a great impact on how you conduct an investigation. Even if the first thing that I showed you for designing, forming questions, asking questions, right? Just incorporating mathematics already changed the nature of what kind of questions you ask. Okay, so we've got a good graph. Now I'm ready to build my model. So let's see, what does my best fit curve look like? What should I pick? Linear, right? It looks linear. Okay. Now I've got constant and coefficient. What should I try and change?
Coefficient.
Coefficient, yeah. So let's see how good can I go? Oh, that's the constant. Let's see, let me pick this one. Okay, so here we go. Y is 18x, and this 30%. This is my model fit. This isn't too good, right? That's a pretty bad model fit. So I should probably go up a little bit more. Let's see. Oh, 99%. That's pretty good. Okay, that's actually pretty great. What kinds of challenges might students have with this?
So the other way, like, you're basically calculating the slope, but not that because it's like.
I'm sorry, can you speak up?
Well, what you just did was basically determine what the slope of the line was.
Yep.
Without doing rise over one.
Exactly.
Just into this one.
So as I alluded to earlier, right, this is meant to scale back a little bit on the algebra needed. Right, but that's exactly right. You could have done rise over run on this. So the different kinds of difficulties that students might have, right? They might play around with the constant, not understand what the constant is versus the coefficient. They might not even understand what making a best fit curve is. I'm guessing everybody teaches this to some degree, right? This is something like, how do you make a best fit line? Does anybody use an automated tool for having students do this? Yep. What do you use?
I use Excel and sometimes Google Sheets. We have kids make their own solutions with particular concentration in chemistry.
Yep, cool.
And then they have to create a calibration curve, and then they have to identify an unknown solution that I make. And I
Okay.
do like linear regression and a slope equation.
That's pretty advanced. So they're doing linear regression stuff.
The
that's-
soccer's brains explode. Yeah. But they get it eventually.
Yes. So this is one of those design decisions that you can make as well, right? Should I have students do this automatically or not, right? Because you could theoretically just press a button and have the best fit curve done automatically, right? And The reason why we decided to have students sort of do this is one, it's actually a very interesting assessment point, that students struggle with this in different ways, and you actually can't get at this with like a pen and paper assessment. So students like really have these sorts of misconceptions around this. But the second is that we wanted to have them sort of link together and have a feel of what that process looks like of trying to make a best fit curve. Like that's actually meaningful for them, and to tie it into the algebraic equation. So rather than give them that automatically, we turned it into an assessment opportunity and a way to have them sort of play around with and understand, you know, what happens when you change the constant and the coefficient, and what impacts that have and how close you can get the data. Another thing that's sort of subtle in this is that I had mentioned earlier with the simulation that we implemented noise, right? So that when I ran the trial multiple times, that there was some noise in data. In the real world, that's actually right. You don't have to worry about that. There's always going to be some variation anyways. But when you're working in a simulation environment, sometimes you could just have something run the same way over and over again, and it will just give you the same perfect results every time. And what that would lead to is a perfect linear trend, which would mean, you know, perfect fit the data. That's a huge misconception students have, right? You don't want them to have 100% fit every time, right? There should always be some noise in the data because we don't have a perfect way to explain everything with mathematics. We can get really good, 99% is pretty good, but it's not 100%. We don't want them to take away that misconceptions that models must fit data perfectly. They can fit really good, but their models will always have that outward limitations.
What other options do you have besides the linear fit?
Sure. We have, horizontal, linear, inverse, square, and inverse square. Strangely enough, all right, so what is, out of curiosity, what does horizontal mean to everybody?
No change.
No change or
No correlation.
no relationship, independent, right? Independence. This is actually the hardest, out of all of them, I argue that horizontal relationship is actually the hardest to do. Because even if you're doing a linear regression one, what happens when I don't remember your name, but I know you talked about linear regression. When you typically do that, what happens? Do you actually ever get like a perfect zero?
No.
No. You get something that's really close, right? And then what happens, right? Well, is it different or is it not different?
And they don't recognize the line correlates because the points are everywhere.
Exactly.
So they're like, I don't know what this straight line means.
And I'm guessing nobody here does like advanced statistics with correlations and significance and stuff like that, right? That like you can say like, is this significantly different from zero or not, right? Let me dust off my college statistics, right? Yeah, we're not doing that, right? So to actually do something like this, you actually have to somehow have students disprove that it doesn't fit any of the other ones, right? That's complicated. So that's just a little tidbit. So when you're thinking about independence and doing this stuff, it's actually much harder than it would seem. Okay. And so the last part here, I'm just going to breeze over this a little bit quickly, is that we want students to form a claim and then back up their claim with evidence. So what happened? When I changed the amount of gold, I saw that the force of gravity it did have a linear relationship, and this supports my hypothesis. And this is actually going to be really challenging for students too, because they might have an initial idea that it might be different, right? They might have said that it's inverse square or something like that. If we were talking about the orbital distance, right, which is an inverse square relationship, probably they're going to say linear or something like that. This last part here, supporting my hypothesis or not, blows their mind, because what happens when they think their hypothesis was wrong from the get-go? Oh my God, I was wrong. That's the end of the world, right? I didn't get 100%. But you actually did get 100% because you formed a testable question and you learned something by going through experimentation and investigation. So being able to refute your hypothesis and understand when that's applicable is a really powerful tool. And oh, by the way, right, this is what standards expect you to do, in class or remotely. Or remotely. Okay, and I'm going to pick as evidence the best fitting curve that I have. Last part of this is we have students do a claim evidence reasoning write-up. And we actually have this auto-graded for the middle school activities that we have that don't feature using math, but when you incorporate using mathematics, students' minds explode, right? Because now you have to talk about math using words, right? So it's not just equation and plugging and chugging. It's how is my mathematical model that I created, the graph that I made, or the mathematical equation back up my claims. In your own words, right? Has anybody done this, and has anybody had some success in doing this? I'd be curious.
Using
No, just in general, like even in like a lab write-up or anything like that. Has anybody done like claim evidence reasoning type stuff
Oh, yeah. But
with using mathematics or something like that, where you actually have to talk about mathematical relationships?
yeah, well, we added an extra step.
Oh, what did
We
you do?
separated the reasoning and the justification because the students were blending that and not understanding to bring that back to the concept of what you're supposed to be referencing.
Mm-hmm.
So what we added, and put it in terms of, if it was text, when you publish, you reference, you don't put all of your graphs and all of your everything in your text, it's in your appendices.
Mm-hmm.
Okay, you only reference your trends and everything that are most important and put that in the text.
Cool.
Okay, so in our reasoning, what that is that's what you want to bring your reader to.
Mhm.
So those are your bullet points, that's what you want, that's what you do. You still have all your other evidence. So in your justification, you bring in the reasoning
Got it.
with your conceptual,
Got it.
okay? Separating those two made all the difference in the world
That's awesome.
for our students. All the difference in the world. And our scores and everything have.
That's actually really cool, and I wonder if anybody's done any research on that, because that's great.
I've got data behind it if you want it for 2 years now running, and a rubric for it and how to set up and write it.
That's amazing.
So it is freaking fabulous, I'm just telling you.
Okay, so
So-
CERJ.
CRJ.
CERJ. That's a big takeaway from today. Thank you.
So you're welcome.
That's actually really cool.
Thank you.
Could you ask Paul, could you explain again the difference
Absolutely.
between the reasoning and the?
And the justification. What we did is we went through, because a lot of students and even a lot of staff members have trouble with separation with that. And what we did is we approached it as, when you publish, you have all of this evidence, but you do not bring that to the forefront. You only bring your most important into the text that you want the reader to pay attention to. You don't bring it all. So the reasoning are the ones that you want the reader to pay attention to. So what we did is with the student, they only have 1 or 2 graphs. So in the reasoning, what they do is bullet points. There is an upward trend from here to here. And it's a list of things they want you to notice that you immediately saw in that trend. It's the graphic evidence. So quick, fast. Then in the justification, they use that reasoning plus the conceptual learning that they should have done prior. There's your justification.
So what do you expect them to write evidence?
Evidence is your data tables. That is the reading from the text. You had that. The author said John 6 times. Why? Or right for that kind of thing. We do multiple source evidence.
So how many, for instance, typically at my school, we do like 1 sentence for claim, 1 sentence for evidence, 1 for reasoning. You do more like a lab report.
We are,
long paragraph.
in Arkansas, everybody's tested and we're doing this fire. So it's all SEP. It's all science and engineering practices. So it fits these right here. So the evidence, there's no requirement. If we need 3 pieces of evidence, it's what we're gonna say, we're gonna ask for 3. We need 2, we're gonna ask for 2. We don't ask for just 1 sentence. You have to answer my question.
Did you want to go?
Yeah, sorry. I didn't mean to
No.
Sorry.
We also use CERJ. We tell students it's evidence, what trend did you see? What do you notice? What did you see at the numbers? Reasoning is, what does that trend mean? And justification is, what makes you think that's what it means? Like,
Got it.
what are you using in your head? What principles of science make you think?
Got it. That's really interesting. And so,
Same thing.
Yeah.
and so for us, so it's actually kind of interesting. So we actually call the reasoning, we actually call it the J, we call it theory, but it's actually mixed together in that one box. So breaking it out is actually a really cool idea. That's actually a really cool idea. Mutual learning, this is the best. This is like the best part of these talks, is like everybody can learn something, right?
Yeah.
Okay. So, all right, I can come back here. And, all right, so you guys have now seen a design
Bingo.
of how this all works, right? So you have some sense in your minds now of like the kinds of activity, that we're doing, the kinds of using math skills that we're having students doing, where the algebra where we sort of like pulled back on the algebraic skills. And you can probably envision variations of this of this kind of test that would involve more algebra. So for example, having them actually compute the best fit curve and like figure out like what that mathematical equation is, computing like what the quadratic formula might be, things like that. Okay, but I want to kind of turn the attention to, right, so I kind of promised you two things. One, to sort of give you some ideas of like what using mathematics looks like, but how do we get students getting better at this sort of stuff? So again, right, bringing you back here, right, well, how do you handle it in this situation, right? Everybody's doing their own thing. And what we've built into our system is a way for you to track what students are doing as they're working. And it'll let you know not just who's struggling, but exactly how they're struggling. So when you click on a student's name, right, and so they're in the process of graphing their data, right, it'll tell you that Sarah Pensky is struggling to graph their data. Why? They're trials, that should be trials. They're plotting controlled trials, but should plot at least 5 to reveal a trend, right? So what we've done is we've sort of encoded, like, so these activities are automatically assessing all the choices that students make. I probably didn't underscore this enough. All those things that they're doing. We're assessing all those sort of different misconceptions and difficulties that they might have in a very fine-grained way. And we're able to turn that around into actionable information for teachers so that you know exactly who's struggling and how. So, for example here, right, they're having trouble because they haven't picked enough trials to reveal a trend in their data. So you could theoretically go over and help them. And when the entire crowd...
Do they see that feedback as well, so they know like if they're stuck that they need to go?
We have, for the math activities, we haven't gotten there yet. We are developing that now. For the middle school activities, yes, we do. That we have an automated agent that comes in and provides them support and gives them more student-friendly feedback. But yes, we're working on that next part now. As a matter of fact, our latest Department of Education grant is on exactly that.
Awesome. Do they, and this is only because of the nature of the student and probably middle school, but we use NWA Map, and there is an AI system in there where they're just clicking around, and then it times them and goes, you got to go back because you're just clicking around. So there's a time frame in which it knows that they're just clicking to be guessing.
Got it. So we look at all the choices that they make. So if they're just clicking around, it would come up with it would try to figure that out, and it would say probably give them the most basic kind of help. It'd be like, look, you don't even have like an independent variable, right? And it's actually important to note that we actually have that gatekeeping. So I went through that 6-step process. At each process, we actually have that gatekeeping. And why? Because if you don't have a testable question, what sense does it make to go and collect data? If your data are all confounded, how can you graph it? So on and so forth. So we also have these class-wide alerts that let you know, on the whole, if a lot of kids are struggling at the same type of skill, it'll tell you. And so that might be a good time either remotely if you're on Zoom or in person to say, look, let's talk about this right now before we keep going on, right? So it's giving you this like immediate information. And I just want to talk a little bit, so right, this is also talk about presenting some research, right? So, right, I'm developing a product, but I'm also an educational researcher as well, right? And so all the stuff that I'm going to be telling you about is like peer-reviewed published work. So the first thing that we want to do is actually determine, well, is this whole experience even useful? Like, do teachers feel like that they can use it? Does it work in a classroom setting? And what we did is we ran some surveys, just for starters, with 5 teachers and 185 students who use this whole platform. They use the math activities, and they use the alerting dashboard. And what we found is that, students said more often than not, so 0 is, neutral rating, 1 is negative, and +1 is positive, that they say that they learned from the experience. And probably the most interesting thing now, and I've replicated this 4 times, how would you think that students would feel knowing that you are able to look at a dashboard and know how they're struggling, that you're watching them? Doesn't that sound wild? Like you're watching your students and they know it. 4 times I've replicated this, that they're receptive to this idea. They actually like to know that you know when they're having difficulty and that you can come over and help them. Why? Because they don't have to raise their hands and say, I'm the one who doesn't understand. That you can be discreet about helping. I didn't think this going into this research. I was like, there's no way. Middle school kids, early high school kids, they're going to hate knowing. They're going to hate that my teacher knows when I'm struggling. Turns out, not at all. And furthermore, when teachers do help, more often than not, they feel like their teacher's help is helpful. That's a good sign, right? That my teachers are not. That's actually a really good sign, right? And I'm not sure how familiar you are with effect sizes, but these are actually really significant effects. So that's great. Teachers also said that the labs are authentic to how practices would be done, like using mathematics overwhelmingly, and the same with the alerts being usable. Okay. And I'm not going to go over these just for the sake of time, but it's like, there's basically, the key thing is that, when you have an alerting dashboard, it might tell you things about students that you might not realize. That students who you might not think are struggling are actually struggling, because more often than not, you might think that you have your high flyers in your classroom, and that they're all okay. But in reality, they might have some misconceptions, and you might not miss it. You might miss it otherwise, right? So sometimes it's really elucidating things that you might not really know about your students. Okay. So the next thing that we did is this is probably the cooler research, and so this is going to be a little bit more. I'm trying to present this a little bit more like a scientist in an abbreviated version. But what we actually did was we had students and teachers again do this in a synchronous remote classroom setting. So the students and the teacher were all on Zoom, and everybody was working remote. So we did this research while COVID was happening. COVID was like, that is the biggest impact. And teachers use the alerting dashboard, and students use Inq-ITS labs. And we have all kinds of data that we collect, right? We know how students do within the Inq-ITS activities. We auto-score that. We also tracked what teachers did with their alerting dashboard. And we also took verbal dialogue interactions between students and teachers. So we actually had a researcher recording what teachers were saying between their students and what kinds of help that they were giving, in order to really understand how is this whole system actually working and what kind of impact is it having on learning. And what we found is, in a nutshell, that when students were being helped via alerts, that students did get better over time at constructing graphs and applying equations. So if a student had difficulty beforehand and a teacher went over and helped them as a result of an alert, that students were improving. Unfortunately, what we did what's called a match cohort design. We looked at between students who got help and students who didn't, and it looked like all students were improving overall, right? So we don't have a real control effect yet, but we'll talk about that a little bit more. We also noticed too that when we were analyzing the verbal data, that high-performing students were given different kinds of feedback than lower-performing students. And this one's a surprising one that we found, is that teachers reported that they were feeling very uncomfortable providing math help to students. That for some reason or another, like the level of math involved in like understanding with graphs, that some teachers felt really uncomfortable doing that they didn't have necessarily the math background. They understood the content really well, but the mathematics part of it was difficult for them. And I can't, and if you're like, say, like doing this at like a late middle school level, I could understand that. If you're talking about linear and nonlinear and things like that, I could understand that. But also, maybe the teachers also don't understand what kinds of help they should be giving students to get better at this, right? That they know what the problems are, but what's the best way that I should be able to help my students? So just to talk a little discussion is that this actually replicated some findings from our prior middle school study, that feedback given in the moment can support learning. But also the teacher interactions with students were different, but commensurate with findings from prior studies. So in middle school we found that what teachers said actually impacted how well students performed, right? So the kinds of feedback that students were given actually did impact how students were getting better at these sorts of skills. But we also found in high school, like I said, that different feedback depending on the level of students, and teachers might not know what kinds of feedback to give. So when you take all of this together, so the big summary here is when you take all this together, is that it might be a good idea to give some teachers some additional scaffolding and clues and things to say to help them start a conversation with their students, right? So the nutshell here is that knowing who is struggling and how they're struggling enough? You probably need a little bit more. How can I also help my students? What kinds of things should I be saying that are most beneficial to learning? And right, we've got the data now to tell you this, right? Because we've looked at their performance and we've analyzed the voice logs. And so this next part here is what we did is we took all of that information. We looked at what things teachers were saying that were helpful to students, and we've turned those into supports for teachers. So now you can actually get some feedback as well of what kinds of things you should say to help your students get better. So just to sort of elucidate this a little bit, is that the same example from before, imagine that Sarah is struggling to graph their data because they haven't plotted 5 data points, right? The different kinds of things you might say, well, something like you give an orienting support, so maybe the student is really high performing or something like that, and they just need a quick reminder. Well, let's look at the graph. How many data points have you plotted on your graph, right? And it might clue them in to say, okay, well, that's enough. Oh, or maybe not. Oh, crap, I really need more data because I can't see a trend in the data. You could give them conceptual support. You need at least 5 data points in your graph to determine what the trend is. Why? Because if you don't, you can't understand what the trend is because you don't have enough data. You can give more procedural support. You should select at least 5 controlled trials. If you don't have 5 trials, go back and collect more data, right? So it's actually not just giving the concept, it's actually telling them what steps they need to follow in the lab, what do they need to do next. And then there's also what we call like a bottom-out hidden instrumental support. You need to pick 5 trials. Go collect 5 trials. Please collect 5 trials, right? And it doesn't involve any other additional contextual information or deeper understanding. Now, what the best thing to do is, and what teachers do, is they mix and match these, right? This isn't meant to be like you do one or the other. It's best if you can interweave these. And just to give a little bit more example of this is that, let's see, what's this one here? They might have a model with correct function, but none have a fit of 70%. So when you're doing the model fitting, right? Same kind of breakdown. Let's look at the models you created. How well does it fit your data? Remember that you want to be as close to as many data points as possible. Think about how to change the coefficient in just the steepness of direction. All these different breakdowns, right? So this is all the kinds of conversation starters that you can have with your students. And so this is, I think someone asked earlier, I can send out these slides to everybody so that you have all these. Or you can use the system and this is all embedded. But what kind of impact does these tips have? So right here's like the holy grail, right? We did another study with 6 teachers and 212 students, again in a remote synchronous situation. 3 teachers had alerts, and 3 teachers had alerts with tips. And what happened? So again, we did these sorts of performance stuff. We had the interaction logs and the verbal dialogue. And what happened? First thing that we did is we looked at all of what the things teachers were saying, and we codified that into these different categories. So were they giving the orienting help, directing students to a specific practice? Were they giving conceptual help? But there were other things that they were saying too. They were giving content information on specific things about the content area, asking students about the content, and they were also giving feedback like, yes, I did this right, no, I didn't do this right. So we did some other coding as well. And we did this really cool analytical technique. This is called epistemic network analysis. And what this essentially does is it takes all of the data and sort of tries to figure out what things were teachers saying in combination with each other. And the thicker lines that you see are the things that went together more closely. So what you see is without tips, there's that thick orange line there. Teachers were giving more orienting help and technical help, like something wrong with the computer or something like that. But with tips, they were giving more conceptual, orienting, and procedural. Different kinds of feedback. What do you think led to more learning? The tips. Even if you know it, sometimes just having that alerting platform available and then just to clue you in, these are the types of things that I should be saying, makes a big difference. So yes, teachers provided more high-level and conceptual procedural support, and guess what? That is better for improving student understanding and practices or processes. That we actually, when we distilled all the data, so this is Rachel Dickler's dissertation that she found this, right? This is a huge finding. Interestingly enough, in prior research, I want to talk about this too because this is important. The easiest thing to do typically is to default to the content understanding. And that's the easy, and it's typically easy feedback to do. But guess what? In prior studies that we've done, when you give the content feedback, it doesn't lead to better learning of the practices. Focus on the practices, not the content. Teach them how to fish. Makes all the difference in the world. And it does really help them understand the content more deeply. That's a big takeaway for this. And I know it's hard to do. But when you've got a tool that sort of reminds you of this, it's like even if you know this, it still reminds you to do it. It actually helps out quite a bit. Okay. So just wrapping up a little bit, right? We've talked a little bit about how using mathematics is employed. We talked about how alerting dashboards can help you notice. But, and again, providing feedback on the practice is not the content is most useful for deepening students' understanding. And just to give you a little teaser of where we're going next with this kind of work, is that now we're actually incorporating model limitations as well, where students are now building their mathematical models, and they have to talk about the assumptions behind them. We're also adding things about making predictions, so using their mathematical model to make predictions, where we're generating scenarios that specifically break their models, so that they need to address their understanding and their assumptions, and understand when their model fits data and when it doesn't. And we're also doing things too about deepening their content understanding with equations, with the mathematical equations as well, right? So we're taking this math into new, bigger directions because there's so much, it's such a rich area. Okay, and if this is something you want to try with your students, we're actually actively looking for research partners in this area as well. You can email info@Inq-ITS.com, or you can try some labs with your students for free. Thank you. Hopefully this is informative. I know there was a lot of stuff here. There's a lot of stuff here to cover, right? About design and about feedback and stuff like that. And hopefully there were some good takeaways here.
Wow, thank you.
Thank you for everybody for coming. I don't know what time it is. Oh, we got 4 minutes for questions. Yes?
Do you happen to be generating any labs where they actually do hands-on and input their own data as opposed to simulated data?
That's a good question, not yet. We've done some decent work in that, and there is a whole host of difficulty with doing that well. As it turns out, we actually have some interesting design and use programs, but we haven't been working on that for a while. That's a great question.
That was my question.
Oh, okay. That's a great, it's sort of, it depends on your age, but yes, we're not proponents of getting rid of it. I'm not going to say that. What I'm here to say is that there's a partnership. You can get more bang for your buck for but what you lose out on is what you actually get rid of. And we could have made choices in how we have physical graphing and stuff like that. Wanted to have them experience the whole process and not get bogged down in all the things. What happens is the more they lose track of the data. And it's a real design tension of like how you carry what's the investigation and how much you actually make them do.
Yeah, I just would be a great starter and then start getting like, well, let's get into like algebra.
And a lot of teachers do that. A lot of teachers.
Thank you.
Thank you so much. Yeah.
I teach integrated math and sciences.
Oh, awesome. Perfect. Yes.
And so we do a lot of modeling here,